irreducibility in general in the scope of fine-grained complexity. So like a subtitle of this talk is non-equivalence of hardness assumptions. In parentheses, haha results. So I don't remember who coined out this term, but it's haha because it's hardness of hardness. And what I'm like desperately waiting for that someone will actually make a ha result, you know, like.
It was probably Jeff Erickson.
That was my pick, yeah. So yes, hopefully you remember that some problems are hard from Sasha's talks yesterday, and we know why. This is like a huge step up because, like, yes, we can explain why we are horribly bad at designing algorithms. So the whole area is about finding excuses for being bad at algorithmic design or being good at algorithmic design. You should pick one of those. So yes. So first we'll talk a little bit about how fine-grained and coarsely gradient complexities are compared to each other, and then we'll talk about how in general you can prove that something is not SATH hard. And at this point, let me like stop for a second. I will say words like not SATH occasionally, and what I almost always mean is it's not plausible that there is SATH hardness proof. Or you can read it, I would be surprised if you show me such reduction. Or I'll be amazed if you show me such a reduction.
Or something will happen.
Or something will happen. Well, it's usually falls into amazed category. So it's not that I will give you mathematical proofs of non-existence of such a reduction. It's not what we're doing here. We cannot prove that algorithms do not exist. That's what we are really, really bad at. But we can hope to derive some interesting consequences of such algorithms. And that's why I will try to use the word implausible instead of non-existence as much as possible. But in case if I fail in that, you just like know what I mean, right? Okay, we're on the same page. And there we will try to show, in the second section, we will try to show how to use non-determinism as a barrier, like how different properties of non-deterministic complexity can be used to show that something is not SATH hard. And this is probably for the other day. We will try to use some algorithmic techniques to prove that there are no reductions between several problems. Okay. So yesterday you were exposed to this exponential time hypothesis. And so it says that we expect 3-sat not to have sub-exponential time algorithm, which is a fantastic hypothesis, and it has a bunch of consequences. So we know that under exponential time hypothesis or under ETH, bunch of problems such as subset sum, vertex cover, traveling salesman problem, and graph coloring, and many, many, many others, we do not expect them to have sub-exponential time algorithm. This is fantastic. It's great. So we can talk about some other functions, right? For example, we can talk about planar case. If we're talking about planar graphs, then planar vertex cover, planar traveling salesman, and planar coloring, and actually a lot more problems have 2 to the square root and time algorithm, and under ETH we do not expect a better one. We can talk about super hard problems in a very interesting case. We have graph homomorphism, subgraph isomorphism, constraint satisfaction problem. All of those problems we do not expect even exponential time algorithm for that, which is pretty amazing. And finally, we can talk about like polynomial time problems on the other case, k-sum, where you need to find k numbers that sum up to 0, or k-clique or k-orthogonal vectors. Like the brute force algorithm is n to the k, and we do not expect to do much better. So usually, except this part, except planar case, we are talking about beating the brute force. usually such a reduction that there is no better algorithm under ETH, it usually applies to the most naive and most boring algorithm that there is. Graph coloring. I mean, exponential algorithm is okay. You're right. You're right on this one. Graph coloring and traveling salesman. I mean, yes, it's not the most boring algorithms. I agree. But in general, it would be usually the case that when we're talking about ETH hardness, ETH hardness is usually about beating brute force. So let's compare that to what I hope you all learned like some time ago, that NP hardness theory. We found one NP hard problem, NP complete problem. We found like that 3 SAT is NP complete. And from that, we derive that all of those fantastic problems are also NP complete or NP hard, right? And this is like super nice picture. We have one generic approach. We have like one. This is like, as a tree, this is really simple tree. We have a problem that has a bunch of kids, and all of them are NP hard just because P naught is. We do not expect polynomial time algorithm for them, specifically for the reason that otherwise P is equal to NP, and we don't like that for some reason. So let's move to fine-grained world, SATH, strong exponential time hypothesis. There are a few ways to define it, but like usually you think of that like, naively that SAT cannot be solved faster than 2 to the n. I mean, there is a technical definition that required this to be like formally consistent, but yeah, let's just think that SAT cannot be solved faster than 2 to the n. And well, there are actually very few problems for which we can prove that there are no better than 2 to the n algorithm under strong spatial time hypothesis. There are actually not that many of those. There are a few problems for which we can prove that they require n to the k sharp. So the difference is there are no big O. When I'm saying there is no better algorithm, we do not expect n to the k minus epsilon algorithm for any of those problems. Finding k vertices that dominate the whole graph, or finding k vectors that are in some sense orthogonal, it's all hard, and they're all hard up to a brute force, right? So like you finding k orthogonal vectors, well, you find k, you check like all the possibilities, either n to the k of them, you check if they satisfy the condition. If they do, fine. If not, not. But yeah, okay. Then we have like these n square problems. Like there are much more rich theory there. We have this orthogonal vector problem. We have longest common subsequence, added distance, sparse graph diameter, and many more. Like in this subfield, there was like a huge boom of lower bounds. And this is pretty cool, right? And it still looks kind of the same way. We have one central problem that explains a lot. Well, and here's where the problems comes.
What is the set splitting?
Sorry?
What is the set splitting?
Set splitting, if like you want to find you given bunch of sets, and you want to find a subset of the universe such that every set is non-empty intersection with your subset and with its opposite. Sorry? K orthogonal vectors. Okay. So the problem is that people were looking for explanations for hardness of different problems, and they developed fine-grained reductions not only in terms of strong exponential time hypothesis, but they were using other hardness assumptions. And the picture looks more like something like this. I know this is really like hard to read, but let me like walk you through a little bit. And it's supposed to look ugly. That's the main point of this slide, that it's not good. So we have.
Still, can you zoom in into the part that you're going to show?
How? Yeah, I don't think. Okay, I'll just read really loudly and slowly. Okay, so we have this part that is like SATH hard things. Fantastic. This is well-developed area. Everything is great. We have set cover, which has a few consequences here and there, and it's a huge open problem if association and set cover are somehow connected one way or another, right? So set cover is a very important problem. So we're given a bunch of sets, and the question is, what is the minimal number of sets you need to cover the whole universe? And yeah, we don't know any algorithm that is better than 2 to the n, and we assumed that there is no better. Okay, let me stop here for a second. There are 2 ways we can formulate like a conjecture, and it's actually interesting that for set cover we call it set cover conjecture, and for SATH we call it, say, strong exponential time hypothesis. So I had a chance to ask, like, how did that happen? Why they used the term hypothesis? And the idea is that if it's true, it's very interesting. But if it's false, it's also very interesting. Because strong exponential time hypothesis implies algorithmic lower bounds. But not strong exponential time hypothesis implies circuit lower bounds, which is pretty amazing. So if you resolve the question, if you find a better algorithm, that would be amazing. Sorry?
For vertex star, we don't know the better algorithm than for vertex cover.
Vertex cover. Yes, we do, and yes, that's is there by mistake. I'm so sorry about that. Yes, there is a better algorithm. There is a better. Yes, there is a reduction that preserves sub-exponential time algorithm between set cover and vertex cover.
Yeah, the subset sum will also.
There is, yes, but better than 2 to the n over 2 implies yes. Yes.
No, that's not such reduction.
Sorry?
That's not such reduction for subset sum. For subset sum, it is.
Yes, it's a little bit more. Yes, it's faster than the largest. Sorry? Yes. So I think there is a reduction that faster than 2 to the n over 2 times m. If you can improve either of those, okay, I'll check. I'll check that right after the talk. I'm sorry if there is some misinformation there. Anyway, so why we call set cover conjecture? Well, because what will happen when you discover a better algorithm for set cover? Well, you're a truly algorithmic genius, and everything we worked on hardness, under this hardness assumption, will go to trash. That's about it. So we have some really obscure hardness assumption, like Mach 3 SAT. I don't know a single reason to believe in this conjecture except that we tried. But we don't know better than 2 to the n algorithm, and under this conjecture we can formulate some lower bounds. Yeah. Like time algorithms. We have 2 very important problems. We will talk a lot about them. It's all pairs shortest path. I hope the name is self-explanatory enough, so I will not write it down. We're given a graph, and we want to find the shortest passes between every pair of nodes. Okay? We don't know any algorithm that is better than n cube if we allow weight to be sufficiently large. We know better algorithms if weights are sufficiently small. And under this conjecture, we have a lot of lower bounds about graph problems. Like a lot of graph problems cannot be solved faster than n cube or n square or whatever under all pair shortest path assumption. On the other hand, we have a three-sum conjecture. Yes, it's a finding a cycle of length 4. That's a question? Oh, okay. So yes, the other very important polynomial time problem is a three-sum problem. I'm giving you an array of numbers, and I want to know if there are 3 that sum up to 0. So there is like an interview type algorithm that solves this problem in n square. We can solve it a little bit faster than n square, like n square over some logs. But we don't expect, again, we don't know, but we think there is no n to the 1.99 algorithm for this problem. And we have like a body of all kinds of geometrical problems that are hard under three-sum conjecture. And also we know some like, didn't include here, but we know a bunch of dynamic problems that are hard under three-sum conjecture. And also we have this very nice intermediate problem, zero-weight triangle, that is hard under both three-sum and all pair shortest path. This is a problem where I am giving you a graph, and I'm asking if there is, with weights on the edges, if there is a triangle with weight 0. We don't know an algorithm that beats brute force here, so that solves this problem faster than n cube. Well, sufficiently faster. We know something like n cube over 2 to the square root log n, something like that, something really obscure. But no n to the 2.99. Okay. So the main reason I'm here and I'm speaking to you is why we have such a drastically different picture for fine-grained reductions and for why this one is so much better than that one, right? Okay, and this is the actual title of this talk is, yes, we will answer why. So there are actually reasons for that. Okay. First of all, I lied to you terribly. So when we talk about coarsely grained complexity, we are not actually talking about NP completeness theory. It's a lot richer subject than just NP completeness. So yes, of course, we have all these kind of problems that we do not expect polynomial time algorithm under P not equal NP. But there are other problems. For example, there is integer factoring. Integer factoring is not a polynomial time problem. So the problem is formulated in the following way. I'm giving you two numbers, a and b. And the question is there a factor of a that is less than b? Right? And we do not expect a polynomial. Again, we think is unlikely, and we'll talk about how that happened. So we already what we do so the other, maybe even more famous problem is graph isomorphism. Yes. Is not connected to, is not NP complete, and there is no reduction from 3 sat to graph isomorphism unless NP is in in the like classical complexity, right? So there was nothing new. We did it 20 years ago. Just I mean, quasi-polynomial time does not imply that it's not NP-complete on its own. I mean, that would be weird. I haven't seen a single person who actually understands that algorithm. I know, but...
This is also not an NP, right? Because it's quite a polynomial.
Yeah, well, this is cheating. I don't know. Okay, so what we'll do now, we'll stare really closely into integer factoring problem, right? And we'll see why we do not expect a beta, like a reduction from 3-sat to integer factoring. Okay. So here is the definition of a problem that says, say it again, like we have two numbers, and we want to know if there is a factor of the first one that is less than second one. Runs of course there is a polynomial time algorithm in n and m, right? Well, try all the numbers less than m, check if they divide n, obviously. But the input is the numbers in binary, right? So the size of the input is the number of bits, and that's what we denote with n. So the good question is there a polynomial time algorithm? And I already told you the answer. We don't know. This is a very typical answer for whatever questions I'm asking. Typically, the correct answer is we don't know. Okay. So when we don't know the answer, the natural question we can ask is, are there any good consequences of, or like any interesting consequences we can derive from the lower bound or from the algorithm? So what if I give you a polynomial time algorithm for integer factoring? Well, it will be a huge breakthrough in crypto, and people will really appreciate it. You can break like CIA secrets from 70s, which is, you know, just fun, I guess. Well, no one uses those crypto systems now, but like they did some time ago, and this is still valuable information that you might steal, you know, and publish some papers. So whatever you prefer. Okay. So can we find some consequences of this problem not being like not having a polynomial time algorithm? For example, can we derive a lower bound based on SAT? So suppose SAT requires super polynomial time. Can we say that integer factoring requires super polynomial time? And let me point out, that doesn't mean that I want to prove that integer factoring is NP-complete, right? I can base lower bounds on complexity of SAT without proving NP-completeness or anything like that. Like the good example is tautology. Proving that a formula is always satisfied requires 2 to the n, requires super polynomial time under the condition that 3-sat requires super polynomial time. But it's definitely not NP-complete, right? It's co-NP-complete. It means that our reduction can actually make negations, which means that we are not proving just NP hardness, which would make our life a little easier. We can do some weird stuff. Okay? So why? We will not have a proof that it's hard under SAT having not having super polynomial time algorithm, but we can find an excuse for not having that. Why? Well, integer factoring is an NP intersect co-NP. Right? And what we will prove that if there is a polynomial time reduction, how would you prove that integer factoring require super polynomial time if SAT requires super polynomial time? You will give a polynomial time reduction from one to another. Sorry? We will always mean deterministic Turing reductions. Yes, they're actually equal. That would imply that they're equal, yes. Okay. What we'll do now. So this is exactly the moment I stopped making sense. Yes.
It was just
Yes. It would prove either that factoring is yes. It's okay. Once in polynomial time, it can make two instances of B of polynomial size, obviously. Whenever I'm making I can use my own non-deterministic fix to accumulate either non-deterministic algorithm for integer factoring or non-deterministic algorithm. Because I will show you the algorithm, both algorithms in a second, right? Let's just now assume that we know both, right? We know how to solve integer factoring non-deterministically in polynomial time and so whenever I'm encountering an oracle call, well, we have some kind of negative. If we have both algorithms, and I will present them to you, then just prove that result is point. Just given the exponent of this algorithm. Yes. Oh, because I don't need positive and negative. In both cases, I have to be able to simulate the non-intermittent. Yes, we don't have any intuition of how reduction works. So positive, yeah, that would be a positive. But we are asking for like more. Right? So we are given reduction, we immediately prove that reduction in point t, which implies that mt is in point t, which implies that mt is equal to point t, and for some reason we think that so we just believe it. Oh, so I don't want to turn oracle on it, right? The answer. But we can ask our own non-deterministic cube as a white here. We can ask I will want non-deterministic algorithm. But his answer is no, I will want non-deterministic. Right? What we did, what was the general strategy? We realized that each problem to which we have a reduction from SAT has a problem. And the problem doesn't. So our problem is point P intersects NP. This is what we do. Every problem to non-alternative reduction from SAT with problem, then problem is non-NP intersect point. I'll tell you, but this took people many decades to develop. The exponent deterministic algorithm for integer factoring is very complicated. Now, algorithm. One of few things where it is. What is non-deterministic algorithm? Tell me. algorithm. People. What prime? So I'm giving it two numbers, n and m, and the question is there a factor of n that is less than m? Yes. Yes, exactly. We are asking for all the prime factors of n. Right? We are asking for a prime factorization of n. We are checking the multiplicity. If we multiply all of them, they're actually giving n. And here's the hard part. We're checking that they all are primes, right? We can do that in polynomial time. So this is a hard portion of the algorithm to actually check that the given factorization is correct. But fortunately, we know how to do that, and that proves that it's in CoNP. Okay? Fantastic. Oh? Think of CoNP as a proof that the answer is no.
Okay.
It's a lot easier this way. Yeah. Okay? So what we'll do now, we'll just use the same strategy, but we'll use a fine-grained version of it. So we'll find a property x such that all SATH hard problems have x. Then we'll find a problem A, and we'll show that A doesn't have x. And well, that implies that A is not SATH hard, right? Couldn't be easier. So, what would be the fine-grained version of being not in NP intersect CoNP? Well, so so what is the notation? When we're talking about fine-grained problems, we cannot just say a problem. We usually mean some time complexity, right? Like for SAT we mean for SAT we mean SAT and 2 to the n, right? For orthogonal vectors we mean orthogonal vectors n square. So there is so we mean that there is some target time complexity we are dealing with, right? Okay. So, and suppose we have some problem L and some time complexity T, and just think of that as orthogonal vectors n square. So, what I'm saying that our property would be not having both beta non-deterministic and beta co-non-deterministic algorithm. For example, orthogonal vectors have very straightforward non-deterministic algorithm. Which one is? Can anyone tell me? Yes, just guess the pair of vectors, check that they are orthogonal. It takes about log n time to verify. We're all done. But we don't know better than n squared non-deterministic algorithm for orthogonal vectors. We don't know how to prove that orthogonal right? Everybody on board here? Any questions?
Hard problems with 2 to n.
Yes, so I mean, it depends on the problem, right? Like when I say SATH hard, yes, SATH for that, if we have a reduction from SAT 2 to the n to some problem, some time complexity. So yes, what we actually need, there was no formal definition of fine-grained reduction yet, right, in the school. So let me actually write this down. Suppose we have a problem A with time complexity T at AF and a reduction to a problem B with complexity G. So what does it mean if the reduction is fine-grained for those pairs? So for example, when we talked about, so for example, you were exposed to SAT 2 to the n, reduction to orthogonal vectors, n squared. So what was the property of this reduction that allowed us to call it fine-grained reduction? Yes, exactly. So how exactly we will achieve that? We will talk about Turing reductions all over the place. And in this case, we have to be like a little bit more careful about what we're doing. Right? So suppose, for now, let's think that our reduction makes calls of fixed sequence of sizes. This is not necessarily the case, it's just a wide assumption, but so suppose that our reduction makes calls of size S1, S2, and so on up to ST. Okay? And also that the reduction has time complexity H. So what would be two properties that I need from the reduction? Okay. For every epsilon, there is delta.
Such that f of n, or f, what is the size of the problem? What key?
So size of the yes. So let's say we have n.
So f of n to the 1 minus epsilon is smaller than, but there is also n.
No, that's h.
H. Smaller than h, and plus g of s1 to the 1.
Sorry?
G of s1
What's here?
plus.
Plus.
G of s1 1 to the power of 1 minus delta, or maybe and so on. So
Yes. So it's sum up to s. So in fact,
maybe I should solve epsilon and delta.
yes, that is correct. And in fact, we'll do it this way. That just. So we have that the reduction runs in a reasonable time. Yes, so two properties. First one is that some, like the sizes of the oracle calls are correct. That if you do better on the, if you improve each of your oracle calls altogether, they will give you some improvement. And the second one says that, like, well, the reduction itself runs in some reasonable time. All right.
Would be again the same if you write instead of this, you write f of n power 1 n delta, that knows h plus.
Yes, yes, I just wanted to have be like two.
Something is wrong with the signs.
With the signs. And two. Yes. That should be this. Yes, yes. So this would be our sum of oracle calls. It should be better than. This is the actual running time, assuming we have a good algorithm for.
Trying to check make card reduction out of this. Okay, so we have just only one guy.
Yeah. Okay. All set. Okay. So
why do you have the exists delta twice?
it's
So just justify.
no, it's just two different. No, it's two separate statements.
So you mean that alpha does not depend on.
So the second line just means that reduction runs in reasonable time.
Right.
There is nothing complicated about that. All right. Yes.
Is n the same thing as f of a capital?
Sorry.
Is n the same thing as f of a capital?
N is the size of our instance.
Okay, it's not a
No. Okay. So I probably how much time? Like 5 minutes. Okay. I think I will have to stop now. So what we'll do in the next time? We will use the same trick. We will start with we'll take a close look at how reduction works. Suppose we have a reduction to some problem x. And then we'll see again what will happen if we'll try to use a non-deterministic version. Right? So what we'll do, to create a faster non-deterministic algorithm for SAT. And then we'll talk why this is surprising, and then we'll also present the proof that 3-sum doesn't have x, which means that the hard part is that it's a small proof that 3-sum the answer is no, right? That there are no triples of numbers that sum up to 0, which was like the hardest part of this proof. As it was with integer factoring, again, we have this like pretty cheesy 3-line proof that like, well, every problem to which we can reduce 3-sat is not in NP intersect coNP. But the hard part was to actually push integer factoring into NP intersect coNP. So the same trick here. We will pretty simply prove that under reasonable assumptions, all SATH hard problems have X. And the hard part would be to actually provide an algorithm for 3-sum. And I think I will stop now.